The objective of this lecture is to provide the third part of the study of interplanetary orbit transfer. Now, as stated, this is part 3. Now, first what we're going to do is we're going to summarize what has been done so far with interplanetary orbit transfer and then move on to the next step. So, thus far, we've actually looked at the following concepts. So, the following concepts have been developed in interplanetary orbit transfer. The first of these was that we developed what was called an interplanetary Hohmann transfer. Now, an interplanetary Hohmann transfer was one where the transfer took us from the orbit of planet 1, what we call planet 1, to the orbit of planet 2, so the orbit of a first planet to the orbit of a second planet. Now, that was the heliocentric portion of an interplanetary orbit transfer. So this amounted to what was effectively the heliocentric segment of an interplanetary transfer. And then what we did was we took the concept of an interplanetary Hohmann transfer and we developed what were called rendezvous opportunities. Now, these rendezvous opportunities were effectively times or instances when it was possible to execute an interplanetary Hohmann transfer. So these were times when it was possible to execute, or you can think of start, an interplanetary Hohmann transfer. But that basically gave us the middle portion. So these two gave us the middle portion of the transfer. We still haven't done the first and second parts, which is what we're going to study today. So in order to lead up to how we deal with the first and second parts, we talked about the concept of the sphere of influence of a planet or a body. Now, the sphere of influence was a distance from a body or from a central body where the gravitational field of that body was dominant. So if you were within the sphere of influence of that body, then the gravitational field of that body had the larger influence on the motion of the spacecraft. And then when you moved outside of that distance, then the sun actually took over as the dominant body. So in this particular lecture, we're now going to piece together the next parts of this, because if we recall, an interplanetary orbit transfer is comprised of 3 parts. So the first part is departure from a first planet. The second is the heliocentric transfer orbit. And the third is arrival at a second planet. Now, what we had studied previously was this part, the second part. This was from previously. But today, we're actually going to, in this lecture, we're actually going to focus on parts 1 and 3. So this lecture, we focus on the focus is on parts 1 and 3. Now, when we say departure, departure is the equivalent of what we mean as escape. And when we say arrival, that's equivalent to what we mean by capture. So we essentially escape a first planet and we're captured by a second planet. Now it's not exactly that because we have to apply propulsion in order to be able to do that. So the escape actually requires an initial impulse. And that initial impulse gets us out of the orbit about the first planet and onto what's called an escape trajectory or a departure trajectory. Then there's a second impulse that's applied once we get to the second planet to actually put ourselves into orbit about the second planet. So perhaps instead of calling this an initial impulse, we'll call it a first impulse. Now that first impulse, as I said, gets us out of the gravitational field of the first planet and puts us onto a heliocentric trajectory. The arrival, once we get to the second planet, is we apply a second impulse, and that second impulse captures us or puts us into an orbit about the second planet. So this study now is going to involve a few different things that we have to actually keep in mind. But these few things that we have to keep in mind. The main concept of this lecture, so this is the main concept to be able to do this in a systematic way, is what's called the Patched-Conic Approximation. Now you can actually see that essentially what's happening is when we escape the first body, we're going to go from what would be a circular or maybe an elliptic orbit about that first planet to an escape. And an escape means we have to be on a hyperbolic trajectory. When we get captured, we're coming in on a hyperbolic trajectory, but then we're going to apply an impulse which is going to place us into an orbit about the second planet. So these are the three ideas is that for that we put together. Now if we look at these together, we actually have escape means that we go from elliptic, if you want to call it that. We're going to do a circular case, but elliptic to hyperbolic. And then for capture, we're going to go from hyperbolic to elliptic. Now, as I said, in both these cases, we're actually going to be dealing with circles. And then what we do is we bridge these two, the escape and the capture, we bridge them with that second part, which is the heliocentric transfer orbit, which is how we got the interplanetary home and transfer to begin with. So now let's start this concept of what's called the Patched-Conic Approximation. And the way it's going to work is as follows, is that we're going to imagine first that we have a spacecraft in orbit about planet 1. So we have two planets. I'm going to call them planet 1 and planet 2. Now, in order to be able to make this most understandable in terms of notation, in terms of the math notation, I'm going to actually refer to the gravitational parameters as follows. Mu1 is going to be the gravitational parameter of planet 1. And then mu2 is going to be the gravitational parameter of planet 2. Now, this is how we're going to do this. Is first we're going to talk about escape, and then we're going to talk about capture. We're going to talk about departure and then arrival. So let's first talk about planetary departure. So planetary departure, and this is where the patched conic comes into effect, which is that we essentially are patching together conics. So let's think about what this means. Is that on the departure, since we're going from elliptic to hyperbolic, that means that the hyperbolic portion has to be patched, I'm going to put it this way, with the heliocentric elliptic portion. So there's the first patch. On arrival, we're going from hyperbolic to elliptic, so then there has to be a patch, which is we're going to patch the elliptic with the hyperbolic capture. So this is hyperbolic on departure and hyperbolic on arrival. And essentially what we're going to do is we're going to look at the conditions where in this approximation we can bridge the gap between that exit hyperbola or that departure hyperbola with the heliocentric elliptic portion, and then the heliocentric elliptic portion, so I should put here heliocentric elliptic portion, with we're going to bridge the gap between that and the hyperbolic portion that when you come in or you're arriving at the second planet. So we're going to look at two things. We're going to look at planetary departure and then we're going to look at planetary arrival. And you'll see that these actually have quite a few similarities to one another, which would make some sense because they're kind of opposites of one another. So the first thing that we're going to do is we're going to draw a picture that should help in the discussion for later on. So we're going to start with planetary departure, and then we're going to move on to planetary arrival. So let's look at planetary departure, and it's worth having a picture first from which we can actually build all the equations that are going on. So imagine that we have a planet. I'm going to call this is planet 1. Okay, so this is the orbit of planet 1. And the planet is moving sort of depictively to the left with a velocity vc1 because it's in a circular orbit. And what I'm going to do here is I'm going to draw sort of schematically the orbit of planet 1. So that's the orbit of planet 1. Now, at the edges over here, this is the sphere of influence of the planet. So if I was to draw this, I want to draw a big picture, so it's hard to draw the entire sphere of influence. But this is the sphere of influence of this planet 1. And this is planet 1 itself, and that's the orbit, and this is the orbit of planet 1. So here's the orbit of planet 1. So let's depict it here. Orbit of planet 1. And then the direction to the sun in this diagram is this direction right here. So this is to the sun. So now what we're going to do is we're going to see that the spacecraft is initially in an orbit, in a circular orbit relative to this first planet. And what's going to wind up happening is the spacecraft is going to get placed on a hyperbolic departure trajectory. So this is going to look as follows. So in order to make that a little bit more possible, let's write this a little bit smaller so I have just a little bit more space. So I'm going to write planetary departure. Now, here is the asymptote of this hyperbola. Because remember, a hyperbola is an escape orbit. So what's going to happen is somehow there has to be an impulse that's going to put this spacecraft onto this hyperbolic trajectory. Now I'm going to call the velocity that actually takes this thing out away from this first planet. I'm going to call that V infinity, and I'm going to define V infinity in just a minute. And then what I'm going to do is I'm going to draw this angle, which is the angle of the hyperbola. If you recall from hyperbolic orbits, this angle is actually beta. Now, what we're going to do is we're going to use this information to actually construct this escape. So V infinity, so it should be careful, V infinity I is the hyperbolic excess velocity of the spacecraft as it leaves, or I should say as it departs planet 1 on the outbound hyperbola. So I'm going to call it the outbound hyperbola. Now, what's also important to understand in this diagram is that we're going to be looking at planetary departure. We're going to consider this case. We're going to consider the case of going from an inner planet to an outer planet. So what we're really doing is we're going from a planet that has a smaller orbit to a planet that actually has a larger orbit. So that's the case that we're going to study in this lecture. Now, given all of this, we can actually now say that V infinity, which is equal to the magnitude of V infinity I, which is the hyperbolic excess speed. Now, using that information, what we're going to do is we're going to patch. This is where the patch comes in. We're going to patch V infinity to the speed of the spacecraft relative to the sun as it departs the orbit of planet 1 on an interplanetary home and transfer. So what that means is that there's this excess hyperbolic speed, and you can see when you look back at this diagram that it's going to be effectively tangent to this asymptote, because this is the asymptote of the hyperbola. And what's going to happen is that we're going to bridge the gap between that and the value of the velocity as we actually leave on an interplanetary home and transfer. So if you remember, when we did an interplanetary home and transfer, if I have these two orbits, this is the orbit of planet 1 and this is the orbit of planet 2, that first delta V, call that delta V1I, put the spacecraft onto an elliptic transfer orbit that made its way to the orbit of planet 2. So these two circles are the orbits of planet 1 and the orbit of planet 2. So that means that if V infinity has to somehow be equivalent to this delta V1, where delta V1 is the magnitude of delta V1, because you can see that the magnitude of delta V1I, because you can see that this is actually tangent. This is actually tangent to the circle at this point. So as a result, there has to be a correspondence between these two. And it turns out that in the Patched-Conic approximation, so this is the Patched-Conic, this is how it works, is that V infinity is actually set equal to delta V1. That basically preserves the continuity on the from the escape of planet 1 to the interplanetary segment, or the heliocentric segment. So we recall, so let's recall here, that for an interplanetary Hohmann transfer, delta V1 is actually equal to, well, if we remember the equation for the interplanetary Hohmann transfer, it gave us the square root of mu s all divided by r1 times the square root of 2r2 all divided by r1 plus r2 minus 1, where mu s is the gravitational parameter of the Sun, and r1 is the radius of the orbit of planet 1, and r2 is the radius of the orbit of planet 2. Now, given that that's the value of delta V1, we know that delta V1, in order to patch the conic, has to equal V infinity. So that implies that V infinity is equal to the square root of mu s over r1 times the square root of 2r2 all divided by r1 plus r2 minus 1. Now what we can do is we can actually use this to be able to figure out what is the delta V required to be able to get us out of the orbit of planet 1. So this is the important concept, is that we want to determine what I call delta V escape, where delta V escape is the magnitude of the impulse required to place the spacecraft on an outbound hyperbola and with the right speed of the correct speed on the orbit. Now, what is that speed? Well, that speed is the one that matches this impulse, delta V1. So V infinity is that speed, and that speed has to match this delta V1. So now we have to figure out how we can figure out the impulse. So we know that relative to planet 1, the periapsis radius of the outbound hyperbola is given as follows. We know that RP is equal to A times 1 minus E. But we also know that this actually gives us that that's actually equal to P over 1 minus E squared times 1 minus E, and that's equal to P over 1 plus E. Alternatively, that's the expression. But we also know that P is equal to H1 squared, H squared divided by mu 1, where H is the magnitude of the angular momentum of the orbit. And so as a result of that, we wind up getting that RP is equal to H squared all divided by mu 1 all divided by 1 plus E. So now what we can do is we can actually use this information to be able to solve for H squared. So we get H squared is then equal to, well, we get A times 1 minus E times 1 plus E, and then times mu 1. And that actually gives us that this is equal to A times 1 minus E squared times mu 1. So now we have an expression for H. That gives us H squared. Now what we can do is we can actually use the energy. So we know that the specific mechanical energy of the outbound hyperbola hyperbolic orbit is given as, so we know that E is equal to VI, and now this is going to be evaluated at the right point. VI dotted with VI over 2 all divided by mu over R. And that has to equal minus mu 1 all divided by 2A, where A is the semi-major axis of the outbound hyperbola. So now we can use that information to actually figure out the next step, which is that we know that R approaches infinity on the outbound hyperbola, because we're actually just continuing to go further and further away from the first planet, which implies that E is going to approach V infinity squared all divided by 2, which comes out simply from the fact that VI dotted with VI is going to equal V infinity dotted with V infinity, which is V infinity squared over 2, and that has to equal minus mu 1 all divided by 2A, from which we can actually solve for this for V infinity squared. Now this looks a little bit strange when you actually look at it, because this is equal to minus mu 1 over A, and you say, well, that doesn't make any sense because we have a negative sign there. But recall that A is less than 0 for a hyperbola. So as a result, that's actually a positive number. So then from there we can actually solve for A, which is equal to, and you can see that we get minus mu 1 all divided by V infinity squared, which is indeed less than 0, which is exactly what we want. Now what we can do is we can substitute that result into H squared. So then, if you look back, we have an expression here for H squared. So now we get H squared is then equal to minus mu 1 all divided by V infinity squared. That takes care of that, times 1 minus E squared times mu 1, which is then equal to minus mu 1 times 1 minus E squared all divided by V infinity squared, and then that has to equal, in turn, mu 1 times E squared minus 1 all divided by V infinity squared. Now the reason that I wrote it that way is because we're on a hyperbola, right? So on a hyperbola, e has to be bigger than 1. So e squared minus 1 is going to be bigger than 0. So that actually gives us a positive number. So this number is actually greater than 0. And now what we can do is we can actually solve for RP. So then we get that RP is going to equal, well, it's going to equal this entire expression, which is going to be mu1 squared times e squared minus 1 divided by mu1, the whole thing divided by v infinity squared, and then the whole thing divided by 1 plus e, where I just did the full substitution to be able to get RP. So that whole thing simplifies to, we get mu1 times e minus 1 all divided by v infinity squared. So there's the radius of periapsis. Now we can use this to solve for the eccentricity. So solving for e gives e is then equal to 1 plus RP v infinity squared all divided by mu 1. And in fact, that is greater than 1. You can see that that has to be greater than 1. So now what we can do is we can solve for, we can come up with an alternate expression or a simplified expression for h squared. And then we can solve for h. So then we have h squared is going to equal mu1 squared all divided by v infinity squared times, now we're just going to start substituting in, we get 1 plus RP v infinity squared over mu1. This whole thing is now going to be squared minus 1, so that's e squared minus 1. And so then that equals, now if we simplify this, we get mu1 squared all divided by v infinity squared times, and if I expand this out, I get 1 plus 2 times RP v infinity squared all divided by mu1 plus RP v infinity squared all divided by mu1 squared minus 1, which is then equal to mu1 squared over v infinity squared times, and you can see the 1's cancel, and so we're going to get 2 times RP v infinity squared over mu1 plus RP v infinity squared over mu1, the whole thing squared. Now we can simplify that, and you can see that the RP v infinity squared over mu1 is going to come out of the whole expression. So therefore, h squared is then going to equal mu1 squared over v infinity squared times RP times v infinity squared all divided by mu1, and then what's left over is going to be 2 plus RP v infinity squared all divided by mu1, from which we actually get that h squared is going to equal, well, several things cancel here, so we get mu1 times RP, because the v infinity squared cancels and one of the mu1's cancel, and we get 2 plus RP v infinity squared all divided by mu1, and then that can actually be rewritten this way, which is that we can actually factor out the RP over mu1, and we actually get mu1 RP times RP all divided by mu1, and now we get here, so if you factor out the RP over mu1, we're left with v infinity squared, if I rearrange the terms, plus we get 2 mu1 all divided by RP, and that winds up being the expression that leads us to the most simplified form of this specific angular momentum squared, which gives us v infinity squared plus 2 mu1 all divided by RP. So now we have an expression for h squared, which means that h, because it has to be positive, is going to be rp times the square root of v infinity squared plus 2 mu 1 all divided by rp. So now we have an expression for the specific angular momentum. But we know the following. So now this is the next thing is. So at periapsis of the outbound hyperbola, we have that h is equal to rp times vp. And the reason that that's true is because r and v are, the position and velocity are orthogonal to one another at that point. So we wind up getting that the radius of periapsis times the speed at periapsis is actually equal to the magnitude of the specific angular momentum. So from there, we can actually write that h, which is equal to rp times vp, is going to lead to the following expression, which is vp is actually equal to h over rp, which is equal to the square root of v infinity squared plus 2 mu 1 all divided by rp. And now we actually have this speed right here is the periapsis speed on the outbound hyperbola. So this is the speed of the spacecraft at periapsis of the outbound hyperbola. So that implies that that is, and this velocity, which corresponds to the speed, is tangent to the orbit. So if we actually look, if we say here's planet 1, and here's the orbit, and here's that outbound hyperbola, which I drew before, this velocity is tangent to the orbit. So this is the periapsis velocity. And so the speed corresponding to it is going to be such that when I apply a delta v, so delta v, which is now the escape delta v, is going to equal v plus minus v minus, where v plus is equal to vp. And what we're going to do is we're going to assume that the spacecraft is in an initial orbit, which is circular. So an initial circular orbit of radius rp, which gives us that would actually imply that v minus has to equal vc1, which is equal to the square root of mu over rp, or mu1 over rp, which implies that delta v escape is equal to this vp minus vc1, which is what we actually have. And so when we actually simplify this, then we have the delta v escape is equal to the square root of v infinity squared plus 2 mu 1 all divided by rp minus the square root of mu 1 all divided by rp, which simplifies to, we just get the following much simpler expression, which gives us delta v escape is equal to vc1 times square root of 2 plus v infinity all divided by vc1 squared minus 1. So that is the escape delta v. So this is the delta v, this is the impulse required to place the spacecraft on an outbound hyperbola that has an excess hyperbolic speed that matches or I should say an interplanetary Hohmann transfer. To planet 2. So that is our delta V escape. And now what we can do is we can actually use this to be able to figure out the asymptote angle. So we know that beta is equal to the inverse cosine of 1 over E, where E was derived earlier, and just for so not having to go back through all those pages, where E was derived earlier as E is equal to 1 plus RP V infinity squared, all divided by mu1. So that takes care of everything with regard to planetary departure. Now, what we're going to do is we're going to look at the same case, but this is going to be a little bit simpler now because we actually can look at this in terms of the same quantities that we had before. So now what we're going to do is we're going to look at arrival. So now the picture for arrival is kind of flipped from the picture from for departure, which is this is planetary arrival. And again, we're dealing with the case where we're going from an outer planet to an inner planet. So what planetary arrival looks like is that here's the orbit of, let's move it down a little bit. Here's the orbit of planet 2. Now, planet 2 is actually going to be moving with a circular speed in this direction, which is going to be labeled VC2. Now, given that that is the velocity, we now have an orbit. This is the final orbit that we're trying to get the spacecraft into this particular orbit. So what happens is that the spacecraft comes in on a hyperbola, and then it meets up with this orbit at the periapsis of this hyperbola. So here is this sort of midline, if you want to call it, of this hyperbola, and here is the asymptote of the hyperbola. So where these two meet up, this angle now is beta. It's the arrival angle now, and this coming in is what I'm going to call V infinity minus. Now, if we were to not do anything, if we were not going to apply a delta V at this periapsis location, what would wind up happening is the spacecraft would depart on this hyperbola, and it would just keep right on going. It would go right past this planet. And this would be the asymptote of the outbound hyperbola, which is if we didn't do anything at all. But we're going to apply an impulse here. So this impulse is going to be a second impulse, which is going to put us into this final circular orbit. Now, this second impulse is going to be called delta V capture. So this is our capture impulse. So it's not going to go out on that hyperbola. It's going to get put in to this orbit. Now, in this diagram, this direction right here is the direction to the sun. So actually, let me move this impulse over just a little bit so that we don't get too much interference here on these pieces. So here's the impulse. Here's this. I'm going to move this over here. This is delta V capture. And then this direction right here is the direction to the sun. And so you can see that the orbit of planet 2 is actually something that looks somewhat like this. This is the orbit of planet 2. So this is the orbit of planet 2. So now we can go through the same excursion with planetary arrival as we did with planetary departure, which is that so as the spacecraft enters the sphere of influence of planet 2, it moves with a hyperbolic excess velocity v infinity minus. Now, we know that the corresponding speed, so v infinity, is the magnitude of v infinity minus, which, interestingly enough, is also equal to the magnitude of v infinity plus. So if I call this speed as it departs, if I call that v infinity plus, because that's a hyperbola, those two are actually the same. V infinity minus is actually equal to v infinity plus. So we're just going to refer to this whole thing as v infinity. Now, again, we're doing a patched conic. So we're going to patch the conic. So patched conic means that the v infinity, it has to match the delta v2 of the Hohmann transfer, where delta v2 is the second impulse of an interplanetary Hohmann transfer. And that's because, again, we're doing the exact same thing we did earlier, which is that we're matching the hyperbola and the inbound with the delta v that actually took us on the interplanetary Hohmann transfer that got us to the second planet. So that means that we're going to refer to delta v2 as the magnitude of delta v2I. That's the second interplanetary Hohmann impulse. And so as a result, we can do this calculation again, which is that we know that delta v2 is equal to the square root of, this is the result we get from the interplanetary Hohmann transfer. So I'm just restating this. This is what we derived in the earlier lecture on the interplanetary Hohmann transfer. So that's the delta v2, and that has to equal v infinity. So now, given that that's what v infinity has to be, we can actually compute everything. So we know then we have, so a bit of this is like a little bit of restatement, but we know that Rp has to equal A times 1 minus E, which is equal to P over 1 minus E squared times 1 minus E, which is equal to P over 1 plus E. Separate that a little bit. P over 1 plus E, and that has to equal h squared over mu 2, all divided by 1 plus E, where we recall that mu 2 is the gravitational parameter of planet 2. So when we go through all this and we solve for the for this, we actually get the exact same result that we got before. So using the results from planetary departure, we have that h has to equal mu 2 times the square root of e squared minus 1, all divided by v infinity, which we had actually written it perhaps a little bit differently because we actually wrote it in terms of h squared, but I just took the square root of everything just because it's a little bit more straightforward. And then again, as we use the same conditions that we had before, and we get that E has to equal 1 plus RP times V infinity squared, all divided by mu 2, which is again greater than 1, and that's the arrival eccentricity. And so as a result, we can actually get that H is actually equal to RP times the square root of V infinity squared plus 2 mu 2, all divided by RP. Now all these results that I just got are exactly the same as what we had, at least as in terms of their mathematical form, to the equations for the planetary departure case. Now we're dealing with planetary arrival. So now again we can go through the same. We can do the same thing we did before. At periapsis of the inbound hyperbola, we have that H is equal to RP times VP. So we can solve and we get VP is equal to H over RP, which is just equal to the square root of V infinity squared plus 2 mu 2, all divided by RP. And now we can compute the capture impulse. So we know that the capture impulse delta V capture is given as delta V capture is equal to V, and I'm going to call it, for lack of a better, I'll call it V2 plus minus V2 minus, or we could just call it V plus minus V minus, where V minus is actually equal to the, because it's got to be greater than 0. Remember, this is a magnitude, so it has to be greater than 0. So it's the absolute value of these, which has to be bigger than 0. And we actually get that V minus, in this particular case, is equal to VP, and V plus is equal to the square root of mu 2, all divided by RP. But it turns out that the way we have this set up, VP is actually bigger than the square root of 2 mu over RP. So that means that delta V capture is actually equal to V minus minus V plus, because that's what's actually bigger than 0, which is equal to VP minus VC2, and this is equal to VC2, which gives that delta V capture is equal to the square root of V infinity squared plus 2 mu 2 over RP minus the square root of mu 2 over RP, which gives delta V capture is equal to VC2 times the square root of 2 plus V infinity, all divided by VC2 squared minus 1. So that just basically, that last result just simplifies down to what I have here. So, and again, beta is equal to the inverse cosine of 1 over E, where E is the result that we had from previously, which is equal to 1 plus RP times v infinity squared, all divided by mu 2. So realize that now this completes the discussion of this is planetary arrival and planetary departure. And this case is from an inner planet to an outer planet. The conditions are quite similar when you go the other direction. It's just the equations look essentially the same. It's just the question of how you actually accomplish the transfer. You actually have to come in on the other side of the planet in order to be able to do a transfer from an outer planet to an inner planet, but the equations wind up being the same. So that's why it doesn't matter which one you consider. You get the same result in terms of the structure of the solutions. So this is again what's called the Patched-Conic Approximation, and what it is it's a way of being able to bridge together the conditions for a planetary escape and a planetary capture. So a departure and a capture. That's the idea, and that's where we're going to end this particular lecture. The next lecture we're actually going to talk about what happens in this case where, go back to this picture over here, what happens in this case where the spacecraft does not actually get captured by the planet with a capture impulse, but it actually does what's called a planetary flyby, and it continues on moving beyond beyond this planet, and it continues to move further away on an outbound hyperbola. How we actually set the conditions for a proper planetary flyby. But that's the end of this particular lecture for Patched-Conic Approximation.